or to drinks, wherever. So I'll talk about the inliner in MLIR. And this presentation would be useful if you are trying to use it in your own dialect, or you run into some problem and you're trying to understand why the inliner is behaving the way it is. So rather simple, but we'll get into some details which will help you when you're actually doing development. So as we've heard over the last 2 days, MLIR is highly diverse, extensible, compiler infrastructure. So, and there are many dialects at different abstraction level and ops with various semantics. Now, each dialect understands best what it's about, what the ops do, and each dialect could implement transformations on its own for itself. But then you'll end up with a lot of duplication, and certain transformations is abstracted out and implemented one tested stuff, basically code reuse. But then the challenge is each dialect has own semantics, different abstraction level. How is that possible? Not for all, but for some cases, it could be possible, and inlining is one of them. And we'll see how MLIR solves this problem in general and how that maps to inliner specifically. And then we'll talk a little bit more into the details of inliner, how its operations, and compare it with LLVM, for example, and conclude this talk. Right, so I'm going to take this running example so that we are grounded in terms of what we're really talking about. So on the top, what you say is the affine dialect, and very simply, it's an Affine.for in the gray box. So what you got above is an Affine.for, and in that loop, 0 to 10, you got a load from memref B and A. So basically what's doing is it's got these arrays, you can think, it's loading two scalar values, adding them up, and storing the result back to B. I'm spending a little bit time on this because it's a running example, and we'll develop on this. So this is what it's doing. And the code that you see below is the LLVM IR that's generated by lowering the Affine.for above, first into the LLVM dialect inside MLIR, and then generating the LLVM IR that's the LLVM usual compiler backend can take it. Now, the thing to notice is the LLVM, if you see, okay, we are all familiar with it, we see the different instructions, but these are different instructions, and these are in the language reference. If you were to implement, let's say, the inliner, or when the inliner for LLVM was implemented, you knew this ops, what they would do. So the call op, you would expect a call, you would know what a get element pointer, etc. is. For the MLIR ops, if you're implementing the transformation or inliner, you're wondering, what ops am I going to be dealing with, etc.? What would the semantics be, right? And then the question is like, okay, is there some structure to it? Okay, the semantics may not be available to me as a transform writer, but is there a structure? And yes, there is a structure. And just what Alex was showing previously, okay, this is a table gen description of the Affine.for. So things I want to highlight here is like, so no matter what your semantics is, it would have this kind of structure where you have a set of arguments for your op, a set of results, and 0 or more regions that you have. In this case, the Affine.for has a region with one basic block. And then at the top, you see a list of traits and interfaces. We'll talk a lot about interfaces, so I'll just talk about traits a bit here. Traits are constraints or properties. So in this case, for example, the one in red is an implicit affine terminator. So this op says my terminator is implicit, and it's a specific subclass of the terminator, which I call the affine terminator. And the properties, whatever it means, is you can go and look up in the table gen. A simpler example would be like commutative. So if you're doing an operation that's you converting A plus B to B plus A, you can probe and ask, is this op a commutative op? Right. OK. That's simple. Another way to see an op is this very useful one when you're doing development, is to run this dash MLIR print generic. For the same affine in the upper right that you see there is a pretty printed Affine.for, and the ugly real detail form that is the one that you see below. These are the two same things. So things I want to highlight here is like the step, if you see in the Affine.for, that's implicit, so you don't see it. But if you see it in the attribute, step equals to 1. And then you see some other things that you can map, etc. The point is, the ops in MLIR will have certain structures. And then we talked about the traits, and then we'll look at interfaces, etc., and how that maps. OK, so we get a kind of feel like, OK, we could do inlining, and MLIR has all the hooks and interfaces and stuff. Another question could be, is it useful to inline? What is it? Because a question could be like, you generate LLVM in the end. LLVM has an inliner, so why bother, right? So here's one example, and it's true, like not in all cases it will be useful, but in many cases it might be. Yeah. So here's a simple example. At the top, you've got this func foo. It calls two functions, foo1 and foo2. Foo1 has a code similar to the one we saw before, but in this case, it's got two nested loops. What it's doing is it's got this memref A or array A, it's two-dimensional, and it's running through one row, sums it up, and writes the results to B. So it's just kind of a reduction. And then you got the second foo1 right at the bottom. What it does, I mean, this is a toy example, but to highlight something, so it's not really well-written code. So on purpose. And the foo1 reads B and writes to C. So what we want to do, we see, OK, the producer and consumer are far away. First, you want to inline and fuse. So you want to inline, so this is the way you could run the inliner and see the results. So you say inline, and then what we see here, OK, it has inline. The foo0 and so foo0 is there, foo1 and foo2 are gone, and you see these two loops, one after the other. OK, no big deal. And then we want to fuse, so we say affine foo, and then it collapses it. And you see now, like, the producer and consumer are close. So, OK, there's be many cases where inliner would be useful, right? Having tried to sell you that, and let's see how actually it's done. And now we come to interfaces. So a lot has been said about interfaces, but there's some aspects of it for inliner that I want to highlight here. OK. So interfaces are a generic way of interacting with IR. It's a cornerstone of MLIR extensibility. And it provides information to the transformation and analysis pass. So a way to think about it, like if you are asking a person, tell me about yourself. The person could tell you a lot of things. But you may not be interested in all of it. Better question to ask would be, which MLIR dialect are you working on? Then you get an answer that you really care about. Translating it to inliner, an op would have all the semantics, whatever it is doing. The inliner cares about certain aspects when it's trying to inline. Is it legal to inline this op? How do I inline this aspect? So when you're implementing interfaces, is the op the best, or the dialect the best one to define the interface? Not really, because it doesn't know what question to answer. So in this case, for example, a good place is the inliner itself. The inliner defines the interface, and anybody who wants to get inline must implement those interfaces. And then the inliner transformation works with those. It knows anybody who wants to be inlined would have those interfaces, those methods, and then it can use those to implement it. And that's the whole story. Now we'll see how actually it's done. So I'm writing the inliner transformation, or any transformation. So I define the interface. So there you have it, the DialectInlinerInterface interface. It's an interface defined by the inliner. So that's why you have the inlining utils.h, where it's defined. It inherits from the dialect interface. So it's an interface, but interface for the inliner, defined by the inliner, right? And it has two parts to it. So when you're inlining, you're writing inliner, you want to know, is it OK to inline? Is it legal to inline? And it answers yes, the actual dialect. OK, fine. I want to inline it, but I don't know how to handle this aspect. So for example, here, I can't handle this part of the terminator. Can you tell me how to do it, right? We'll see a little more on these things. So it defines these two hooks. So whoever wants to get inline, that at the dialect level, because you don't want it for op by op, at the dialect level, you specify ops or methods. Is it legal to inline, how to inline, and stuff. OK, so that's still like something you have defined, how actually to use it. And I think most of us in this room are most familiar with LLVM. So why not give an example of how LLVM dialect in MLIR implements this Inliner interface. So there you have it. So you got this LLVM inlining.cpp. If you look in there, you got this struct LLVM Inliner interface. It inherits from the DialectInlinerInterface interface we saw previously. So in this one. So the LLVM inherits from it. And you can already start seeing, if you're familiar with LLVM, the attributes, no duplicate, no inliner, those things, you're going to deal with those. And then it comes back to, OK, when inlining, the inlining transform, the optimizer will ask if it's that op is an LLVM call or any op and wants to inline, say ask, is it legal to inline? And what should LLVM check? The LLVM dialect should say, I know how to, yes, it's legal to inline a call if you have lowered it properly, and this op is actually an LLVM call or invoke, right? So that's what it's checking there. The next it will check probably down. I didn't show it here. It's like the callable. So something, you have a call and you're calling something. What you're calling also should be an LLVM function. Then these two tie together. Then it will go on further and check, OK, those attributes, et cetera, are everything complying? So that's the interface part. But when you have you are implementing the inliner, you're building the call graph, which means you need these calls and who you're calling. But actually, it's not just the calls are not just for the inline purpose, right? So if you have a dialect and you have a notion of something you want to call, and why do you normally call something? Because you don't want to duplicate that thing several times. Then you need to implement these two interfaces. One is the call interface. So in this case, you can see it's not a dialect interface, it's an op interface. Certain calls are called, like certain ops are called. So the contract is if it's a call op, you're going to inherit from this, then you must, if you're calling something, then you must provide the method, like who is your callee, what are the arguments, and things like that. So you can look at these things up in the call interface.td file. And the mirror effect is, so that just like the call, you have the callable. So if in my dialect, I have something which I think is very similar to a function and will be called by different places, then I need to inherit from the callable. But if I'm a function, I get called, I might return something. So what are the return types? So I need to implement those methods. That's simple as that. So let's take an example. And often, like the calls and the function, et cetera, we use just a built-in dialect, right? So look, here's the example. So the func op itself defines a CallOp, and it says that I implement this CallOp interface. So it will provide those functions, et cetera. In your own dialect, if you don't like the func op call, you can do the same thing and just copy some of the code from here and add your own custom code. That's how a lot of cases people do. OK, I want to talk a little about this is legal to inline. So how it works is like this. So you've got the inlining transformer, so the inlining algorithm that's running, and it walks through your ops. Your IR has ops from different dialects. So in the first example we saw, you got the func, the foo, and inside that you got the Affine.for. So what it does, it walks through, and for every op, it probes and calls the handler. So the handler passes. So if it's a Affine.for, it will call the Affine.for dialect and ask, is it legal to inline? And then the Affine.for will walk through its own IR and see, is it a nice simple IR, or am I, for example, in the Affine.for, I mean, this may not be right. Like, am I calling something, or am I doing something that make it unsafe for inline, and it will reject it? If everything works fine, the inliner will get a report back, it's legal to inline, and then it will go and do the inlining. So that's it. That's how the inliner works. If you want to implement it for yourself, you have a DialectInlinerInterface interface, you inherit from that, you define the CallOp interface, the callable interface, and put the hooks together, and then now it's implemented, you run it, and it doesn't do what you thought it should do. It inlines, but not in the way you wanted it. So you get to debug, and then you want to ask, how exactly is this inline implemented? Because we have this notion, like, in LLVM, I know this is how it works. GCC, this is how it works. I was assuming it would work the same way. Well, I mean, it is similar, but slight differences. So the way the generic LLVM inliner works is it builds each node there is a function, and the edges are the calls. It goes bottom up and works on each strongly connected component. And every time it will inline things. And then it runs an optimizer. If things change, it will go back and inline again. So here's a working example. So you got this function A, B, C. And they don't do much there, but it's a cyclic thing, so it's going to try to inline it. So what the inliner does is has internally this structure that it works with. So you got this call C0, C1, C2, and a call history, an inline history. The first thing you will see if you put minus minus debug is these. So it will look at this code here, okay, and it will say, oh, I found these 3 calls in the SCC. It finds it, and then the first thing it's going to do is inline call 0. The call 0 was a call, okay, sorry. So call 0 C0, you see the bottom there in the blue box, is a call to A. So to inline that body, but the main point is now it gets a new call. Up to now it was C2, it gets a new call. And the call history basically says, where did this call come from? In this case, if you follow the arrow, it says the new call that I got comes from inlining A. Why is this important? Because when it starts inlining, it cries bloating. At some point, so there's a trivial case. So here it says, I'm not inlining 4, 5, 6. So these are the new calls. 4 is OK, because it's calling itself. You say, OK, if it's calling itself, I can get into infinite recursion. Other thing it goes is looks to the call history and sees, am I inlining something which came in because I had inlined the same thing before? So it follows the inline history and sees, oh, I've inlined this. This call is here just because I have inlined, it's in the history. So in this case, call 5 and 6, it says, it's a call to B, and so like if you look at C6, it has the index 3. The 3 is pointing to inline history 3. And in this case, it says, oh, B. So it's got a B in its path. It's a very trivial example, so it's straight away, right? So it sees it in the history and says, OK, I've got to stop now. And it stops, does another level of optimizations. If things change, it will go back and inline things more. Otherwise, it will stop there. And the things that you see on the right-hand side, these are the debug prints. So when you are stuck and you're confused why inliner is behaving this way, just have these debug prints and you can interpret the diagram above you see and what you see written below, there is a correspondence. So this helps you when you are actually stuck and want to improve the inliner in what way. And that's it. This is how the inliner in MLIR works. And thank you.
Yeah, thank you very much, Javed. That was very interesting. We have time for 1 or 2 quick questions.
Just because it's legal to inline something doesn't mean it's a good idea. I mean, I guess, are you supposed to bake heuristics into the dialect information also? Right?
Sorry, I didn't get the question.
So just because it's legal to inline something, it doesn't mean that it's a good idea to inline it.
Oh, yeah, yes. You refer
So
to the...
how does it, like, are there heuristics that control it? Or?
So currently, the MLIR doesn't have a cost function. Yeah, that's... Unlike the... Yeah, that's it. Yeah. Thank you.
I think we'll finish here because
Yep.
the closing is about. Let's thank the speaker again. Thank you, Javed.